Okay, in fact, despite the official program, we're carrying on from where we finished last time. Last time we were talking about how to frame a research project, so we've just finished that section up. We started talking about framing good questions, multiple working hypotheses, you'll recall that. And we looked at a particular case study. The question we're having to deal with is, how will we pay to clear for the landslides on our roads? So we set the problem of trying to think what you can measure for that purpose and making that prediction. In fact, the original project I started with just a couple of weeks ago. We looked at some of the factors you can consider, both extrinsic, outside, and intrinsic from within the hill slope system itself. We thought a little briefly about causes and triggers and the relationship between them. And described why roads are right across Asia and in fact all of the continent globe one of the main causes of small to medium-sized landslides in the main. We had our little classroom exercise based on this and the field study. Asked you to think about what variables you would collect. So what are the possibilities? What are the environmental and human factors that might affect the production of landslide debris? Because there's a real temptation for all of us to just list anything, I asked you to think about those variables, how to measure them, and also what actually you're going to get out of the measurement, what benefit it was to you. Then we talked about making variables, saying that quantitative variables, interval and ratio data were the best quality data if you could get them. I remind you of the talk about my students in the field measuring pH when the problem was caused by motorbikes with deforestation, or not deforestation, devegetation in Wales. Sometimes you have to make up variables on the hoof, in which case some of these lower categories are better, and the researcher's friend is the ordinal variables, which you can create without a great deal of thought, and if you're lacking the equipment that you need. We also talked about nominal variables and that they're problematic because since they're categories, they mean that they have to be replicated all the way through your data set. And this becomes important when you think about the next topic we will go on to, which is sampling. So I asked you to think about what sort of variables you were thinking of collecting. One of our favourites for this problem was looking at conditions at a landslide, conditions where there was no landslide, average conditions. I'll show you the results of that later on. And that's a categorical variable because either there is a landslide or there isn't. So now you need to sort them out again. Go back to your multiple working hypotheses. Try to select with them variables that match the hypotheses. This is a testing to make sure you're going to collect all the data you need. And again, there's the whole thing of functionality. You're not collecting information simply because you can collect information. For instance, it's very easy to collect pH data, as I said in Wales for the devegetation study. So you could collect pH data here, but there's no possible use to anybody. So why bother? Next thing is a very painful step in research. You have a limited amount of time. You have to be pragmatic. You have to think, well, what can I actually do given the time and resources? Nothing is worse than a half-finished study. You can't do it all. Better not bother. problems with that, particularly if you're adopting a statistical approach, is that you need samples of a respectable size. Small sample statistics apply, they're very specialized statistics. I don't really trust them, nobody really trusts them, but they apply to numbers when you have data in a category below about 23. For safety, I recommend you may have for each categorical variable at least 30 cases. That means you can compare them. So that usually means you need at least more than 70 records for statistical analysis, because if you're comparing, say, yes, landslides where trees are, and yes, landslides without, you will need at least 30 in each category to avoid having... and if you've got maybes in the way there, and you usually do, well, not many trees, or perhaps there's a tree or two, then you need a much larger sample. You'll have to think about how you're going to measure and record each variable, identify its data type. And if it's too hard to get a ratio variable, degrade the quality of the data you're collecting. You have to rely on ordinal data. Yes, no, maybe, type data, even nominal. At this point, you should start thinking, there is very little. It's really a test of your stamina. Like long distance running, doing a field project, collecting data for an inventory or statistical analysis. It's fine when you measure your first data set, and by about 10 you're getting quite good at it at each site. By the time you get to 150, you're sick of it. You hate it. You just don't want to do the next one. It's a real mental stretch to carry on. It's easier then if you cut the list to the ones you absolutely need, so that you're not endlessly recording difficult things of dubious value. Okay, so you've got Prof. Rowett suggested a project yesterday. 2 kilometre stretch of road, we will say. New highway. Maybe it could be the Kohima-Dimapur highway. It's going to be a lovely case study in the next 2 to 3 years. And you look at your 2 kilometres and it's covered with landslides. Some are big, like the one we saw yesterday. Some are smaller. Some are really quite tiny, and you wonder if you should bother with them at all, producing debris only the size of this desk. You have to define a lower level. But if you add them all together, the frequency of the landslides could be in the hundreds very easily. So that's a lot of measurement, even for a short, small-scale study like that, if you're going to pick up every landslide. And you'll see tomorrow the reasons why you should. So one way of doing that is saying, well, I'm not going to measure all of these. I'm going to sample from them and collect only enough that I need for my analysis. And I calculate, because I have 2 categorical variables, and I need these categories filled, that I will measure only 100 or 150. So how do you do that? A population is the universe of all the members of a particular group, and that's your 300. A sample is the part of that population, but a perfect sample should be an exact replica of what that looked like. It's just smaller. It should have the same properties. It should have the same mean, the same data distribution about that mean. And if it isn't, you're collecting a biased sample, which means you're faking the results ultimately, which is a nightmare. You don't want to be there. Not least because someone could come and do the same project and contradict everything you said. Statistical hypothesis testing usually takes the form of what is the probability that this sample came from this population, or what is the probability that these two samples, if you're testing categorical variables, came from different populations. So what sampling strategies are there? This is one that gives, I've got lots of grey hairs now, but some of them were created by my students who pretend they did random sampling. And what is meant, they're just going to pick the first ones that came to sight, which is not random sampling. It's maybe accidental sampling. And of course they only pick the ones they like the looks of. So that's even worse, that's biased accidental sampling. If you're going to do random sampling, you have to generate the location along the road or the coordinates if you're using a map, using random number tables. You can find those on the internet or in any book of statistical functions. And you combine those numbers in the sequence. You can be down the rows, across the road, diagonally, any way you like, as long as you follow the exact sequence that's in those tables. In which case, that's a computer-generated series of random numbers. And they will say where or which number landslide you will measure in this case. It's very quite fun, but it can handle every second landslide along the road. 150 from 300. You could again miss that big landslide yesterday and pick the little ones on either side. And if there are irregularities that match your sampling, so that alternate landslides are on the spur of the road and then the next one is in the embayment, for example, then you could end up just sampling the ones on the spur and not in the embayments in general. So if there are irregularities in the distribution of the data, you can end up with troubles too. But nevertheless, that's quite a good one. Stratified or nested sampling, it complicates measurements and analysis. It means you get data coverage. It means as you go up your road, you say, well, I'm going to collect one data set at the next landslide, one data set between it and the next landslide, something of this sort. In that case, you're going to collect an identical number of samples of landslide situations and non-landslide situations. So that's a stratified type of sampling. Three things affect the quality of the sample. Bias. You must avoid any general error. You have to take yourself out of it somehow. We all want to measure the big landslides. We don't want to measure the little fiddly ones. But somehow you have to compromise with reality. Avoid that bias. Precision. Make the best quality measurements that you can make in the field. And ease of collection, which is the less you have to sweat over collecting it, actually the higher precision you will have and probably the less bias too. So no general error, no bias, no noise in the data and no sweat. That's the way to do it. Okay? Sorry, that's a bit not very scientific language, is it really? Geographical sampling is a special subset of sampling. What you do here is you generate map coordinates where you will sample. Your coordinates can describe a block or a point as you wish. Again, you can use random numbers to generate map coordinates of sample points, in which case you can have a nice square map and for some reason all the sample points are up in the top corner. Perfectly legal, mathematically correct. It's what the random numbers have told you. It's not actually intellectually very satisfying because you know there's 3/4 of the map with hardly any sampling points. Systematic, it's the one most of us adopt. Drop a set of coordinates across your map, sample at each point or in the middle of each square that you've defined, and so on. Stratified, okay, your map's got hilly areas and plain areas, forest areas and no forest areas, agricultural areas, no agricultural areas, urban areas, etc., etc. And you sample within those using one of these other strategies and treat them separately. And there are various Always in this thing, particularly in statistics, there are fancier versions that various people have used. I mentioned some at the bottom, I don't recommend any of them. But they attempt to combine most of them regular and random processes. So here's coming up to your final assignment for my bit anyway, not for GIAN, but for these lectures. And it's exactly what you expect is coming. I'll repeat this at the end. Again, I want one sheet of paper. You could do it alone, but it's much better to talk this through. In practice, when you work in research, you usually have to work in a team, so it's good to get used to negotiating things in teams. I would suggest 3 maximum for this. We had a nice Vans diagram produced by a team of 3 earlier. So that was great, I like that. Right, out your research plan. What you're doing is writing out a research plan for the project that we've described to predict how much landslide debris you're going to have to clear from a stretch of hill road. So you want to collect the variables that are producing the debris and see if you can make any sense of them. So on page 1, briefly, a sentence, 2 sentences is all you should need. Sketch out your multiple working hypotheses, which might be landslide debris is produced by I wrote that's no tree, and then on page 1 and 2, you've got problems. How steep is it? Well, the steeper it is, good qualifications we'll come to later. It's probably more going to be landslide. How high is the road cut? That's probably the same question as that. But when we get above 3-4 metres, we really do start having problems. How much hill slopes about it? If you're close to the slope crest, you're not going to get big landslides as if you were at the bottom of the slope when you have the whole mountain on top of you. Have you got problems with toe erosion by rivers? Activity along faults you would probably include too. These are things we looked at in the field. Are there adverse geological structures? If the rock is massive and any weaknesses are tipping into the hillside, you're probably not going to have much problem. But in situations like yesterday, where there are loads of lines of weaknesses, the rock's very fractured, yep. Do rock structures dip towards the road angles greater than the slope angle? Well, if they do, and there's an area, a grey area in the middle, and it is rock structures rather than a true bed, and then probably you have landslides. Do you have structural weakness, lines of weakness, daylighting in the road cut or the slope in general, particularly faults? Watch out for faults in large joints. Are there many lines? So there are lots of discontinuities in the rock that's tipping down towards the road. Have you got serious weathering? It's not me, really. Are there weak soil or rock layers? You get a layer of clay or something in your rock slope, and she's holding water up. It's going to encourage failure. Any of the materials in the road bed likely to liquefy and become plastic and flow? Do you see any evidence of past landslides? One of our favourite comedians in the UK used to tell stories. Yes, I went to my doctor, he said. I said, Doctor, I have this problem. And the doctor said to me, well, have you had it before? He said, yes. So the doctor told me, well, you've got it again. And it's very much the case with landslides. Were they there before the road cut? Does the actually cross-active slip planes, because if there's something going on already, it's likely to carry on. Tension cracks we talked about. In large rock joints are sometimes tension cracks too. And that's leading you towards landslide. Standing water in these cracks, you've definitely got problems, because that's providing lubrication down them. Water through the rock, seepage. We didn't get any good results when I've done this, because usually it's been too late after the monsoon. But strong seepage is supposedly an indicator of landslide. Again, water seeping along adverse geological structures. Something causing a build of water pressure upslope. Extra loading added upslope. Forest degradation, taking away the strength of roots. Vibration due to traffic. All of these things. Okay. Let's think of some of the other technical problems. Each item on this checklist could be quantified. That's the research we need by direct measurement. Measurements can be meters, degrees, joints per meters, meters per meter squared of vegetation. Notice not percent. If you're doing statistics, you want to avoid percents because they're a closed number system. You can always restate a percent as something else, in which case it's legal to use it. So meters per meter squared for vegetation. Or if you can't do that, you can use your Likert scale, ordinal scale. Very big, big, medium, small, very small. Obviously, it's not going to serve you as well as if you can measure it, but it may be better than nothing. Categorical scale, is there a house upslope, or is there no house? This is a survey from 2010. The owners of the house asking if we're going to get them some compensation for the landslide. My trusty assistants, I don't understand the Hindi, so they were telling them all sorts of stories like that. Anyway, there are big problems sometimes. The biggest problem in converting data is using true bearing. Compass bearing. And this is why. It's a circular measure, 0 to 360. So if you've got a generally north trending thing, you're measuring true bearings of 5 degrees and 355 degrees, for example. When you convert them mathematically to an average, you get exactly the wrong answer. Because the average of 0.5 on this is going to be 180. It's not going to be 360, which is the true average. So sometimes you have to play with your compass measurements in order to make something that makes sense in this case. If I had the time, I would have you resolving how to do that, but it's actually not difficult when you think about it. But it's one to watch out for. The creation of the road cut then, let's look at these in some detail, is the most difficult situation for a road. The new road is most vulnerable at the moment of creation. My first study was on the Missouri bypass, and the first time the monsoon hit that, completely closed it. You couldn't see most of the road depth of the Day-3. At the moment of creation, you've got all the stresses created by the blasting. You've got beginning of pressure released from the rock that's being exposed, weakening joints. You've got the fact that the hill slope upside may or may not be perched securely after you've taken a chunk out of it for the road cut. And all of this, you wonder whether it's going to stay there. And it's being subjected to all sorts of new pressures for the first time. As time passes, unstable sites fail, and as they do so, a lot of the excess energy you put into the hillside begins to disappear. Not always, unfortunately, but sometimes. So you tend to get a changing character and quality of the failure as you go on. This is a study I did when I was at the University of Oklahoma in my early days. And we were looking at road cuts. And this shows part of the problems again of slope brightening. A is a new road cut. Got a nice steep face, you're going to get soil fall and so forth off that. You might get a failure too, but mostly it's soil fall. As you get the soil fall, you start to get the accumulation of the talus slope underneath it, of debris, all built up at its angle of rest, usually a finer weathered material. This is retreating because this is still contributing sediment, so this slope tends to become more gentle. There it is again, lift it over time. As you get the accumulation of the talus slope, in this situation you get the development of channels within it as well. And that's because this is holding water more than the original rock did. It tends to be the finer sediments to the west and wash down. So what it shows is this slope becomes more vulnerable to slumping. That slope is more vulnerable to falling. And you've got a progressive transition as you go through time. So the landslides you start off with, hazard you start off with on a new road, not necessarily the ones you end up with. Steepness. Okay, the more steep a hill slope, the more it is that the resultant of stress and resistance falls outside the ground and you get a failure. One of the interesting things is that people have reported critical minimum and maximum hill slope angles for the types of operations of geomorphological processes, including landslides. And we'll get to an example of that from Rio a little later. It's not yet been done for this region or the Himalaya, as far as I know. There was a lovely study done ages ago, back in 1958, by a guy called McGregor in the UK, who was looking at the way different slope angles were used for what purpose in the country, and he produced a slope angle classification for that. That could easily be done for landslides also. The International Geographical Union has 6 categories of slope steepness. If you wanted, you could use that as a variable. One, either convert them to categories, not categories, to an ordinal scale, a scale of 0 to 5 or whatever you want. When you start looking at things in detail, nothing is as simple as the textbooks are going to tell you. It's one of the laws of life. The field exists only to contradict the textbooks, I sometimes think. Here we have landslide erosion rate across a particular area. I think it's a kilometre area. Again, it's look at that scale. That's a typical logarithmic scale that you see in all of these kinds of studies. This is the effect on the slope angle. Effect of the slope angle. Okay, you can see in each category. The average is increasing in the pre-74 survey, but it doesn't mean every landslide in the lower slope is going to be smaller than one in the bigger slope. And that one is going to be vast and probably means that there was more landslide sediment in this country. This is from a huge study. It's inventories of 15,000 landslides in the eastern Himalaya, which can't be too far from here. I don't know where they were working. Probably Nepal. And from a very recent, relatively recent paper. One interesting statistical test, and of course these are produced by, I think SPSS produces these sort of diagrams for you. The computer routines. If you get the interquarter range separate, so if this were a little higher and there was a gap between the two, or if you compare that with that, you'll see that there's a gap between the interquartile ranges, and that's a good marker of significant difference. So you can say that landslides on this slope are significantly greater than landslides on that slope. Here, You're lucky if you can see there is a difference, but you'd be lucky to prove any form of statistical significance between them, even with a very large data set. So, and the evidence is, again, you can see the interquartile ranges don't overlap. So it's a good rule of thumb, shall we say. Threshold reversal. Take each of these data sets separately. What we're talking about is the number of, landslide frequency with slope angle. This is from Rio de Janeiro. One category. Category 2, much higher. Steeper slopes, but much less landsliding. It happens in both the case studies. Well, the peak is in the same place. So there is a situation that as you get to steeper slopes, you can get less landsliding than on less steep slopes. And there may well be an optimum slope from these diagrams suggest may be controlled by factors intrinsic in the ground that affect that. So slope angle is a very important variable, but it's not always your best friend. There we are. Rio, debris flows above Tersopolis. Very typical forms of them. Some of them there look like they started off as landslides. Maybe that's a debris flow, maybe that's a landslide. It's getting hard to say, isn't it? You gradually define a debris flow on the length of the runout, so that could be a discrete landslide, but that's probably a debris flow because it comes right down here somewhere. That's a discrete landslide up there. So you don't think that's so nice if you happen to be living down here, of course. And you notice again they're forming on what looks like quite well forested slope. There's a bit of deforestation going on there. Not as far as we've got one of the hills on the back that you can see some camels. So the conclusion is that slope angle is important, but it can easily be overestimated, its importance. During severe rainstorms in the Rio case study, gentle slopes of low landslide susceptibility suffer a lot of debris flows. And the reason we've gone through already is the fact that they're often accumulation slopes. And it's the material within them that's causing the problems, and the saturation of the material within them. It's not a very good start to illustrate. Yeah, so clearly there is a sort of hydrological, geomechanical threshold for landsliding, slope failure. The question is how to define it. Shallow landslides are controlled by very different things to deep landslides. Drainage areas, soil depth particularly. It's an interesting attempt back in 2005, the Borger and co. tried to model the impact of roads on shallow landsliding. But they couldn't actually capture this threshold that they were looking for because of various problems, the complications of hill slope hydrology. And the problems include the fact that the bedrock surface probably doesn't correspond to the surface topography. In fact, the way it doesn't correspond to it is often critical because there's accumulations of debris is the difference. But this affects saturation patterns and is devilishly hard to model, even in the field, certainly for remote sensing. Also, you've got strange things that run through most slopes, and very rarely are they exposed like this. And they're natural soil pipes. Some environments they're big enough to walk into. In Wales, you find them under the grass turf, and just about the size you can get your arm into. They accelerate the removal of water, but they complicate the hydrology. And you never know if they're there or not because they're in the ground underneath you. So more complications. Okay, the slope is undermined and not reinforced. Find a lot of these roads now will have retaining walls on them. Then you're going to get a landslide. Same if the river is diverted or diverts itself by meandering against the foot of the slope. Interesting, the effect of retaining walls. Standard retaining wall is built in the Himalaya, at least in the western Himalaya, is about, it's not as tall as I am, it's about 1.5 meters tall, built with solid masonry. And there's an interesting effect on landslides. It's very good at stopping small to medium ones. Absolutely does nothing to the big ones. But it affects the distribution of landslides enough. How high is the road cut? Sometimes that's difficult to observe. This is a road doing a loop here. So there's your road cut. And as you can see, it's contributing debris down the slope, burying this road below. Possibly you'd say that's the height of the road cut, possibly it's up to there. Very difficult to say sometimes. What is important is how much hill slope lies above the road cut, and of course in this case it's particularly important because it's contributing debris. If you walk along here, it would be hard to know whether this is a production of this road or a production of shoveling sediment from the road above. Alfred North Whitehead, famous philosopher, said nature doesn't come as clean as you can think of. It's the difference between the field and reality. Geological structures, we've run through these on an earlier slide. But slides can occur even when undermining isn't active, and this is I'll emphasize this again, because this is something that we don't tend to think about. When you remove part of a hillside, you take the pressure off the rocks that are left in the hillside. So naturally you've created a void and the rocks are able to expand into that void, and they loosen up. In the process they create joints parallel to the surface. This is very dramatic in mining, particularly deep mines, where you find you've driven a mine tunnel through the ground, and if you look around it you can find circular patterns of joints. When you think of failures of mines, you think of the roof falling in. But in deep mines, it can equally be the floor coming up. And it's due to this pressure release process. It's the widening joints. Often joints form parallel to the excavation, and they develop slowly over a period of years. Oh, we've seen this one. We'll see it again because I like it. It's got a nice rock fortune. I don't know why I've done it twice. There we go. It's really a debris avalanche, isn't it? The whole thing is broken out. There's no block moving like we saw before. My brother wasn't in the way of that. How strong is the rock? I think that was why that was in there. You can measure, if you're a geologist, you know about Pito's scale of hardness, how much you have to do to classify a rock. You could use this as a kind of index if you thought it was important. Hard rocks, you have to bash with a hammer a lot. You can break an ordinary hard rock with a hammer. You can scratch a soft rock, and so on and so forth. In general, harder rocks will hold the steeper slopes, but some rocks lose strength more quickly than others when you subject them to weathering. If you look at the material itself, this is their strength measured here. You can see there's a vast difference between hard granite and gravelly debris, even glacial clays. You don't have glacial clays in this part of the world. There's never been glaciation. And this is also represented by the angle which the debris will hold. But it's not a very clear distribution, as you can see. Goes from about 30 degrees up to 45. More gentle, the reason you might want to recall the angle of friction of the debris is because if it's very low, that probably implies water was involved.
first study I did in Missouri, it actually turned out to be a very important variable, but it's never turned up since in subsequent years. This is again the effect of rock. This is a GSI study in Darjeeling. I picked it because it's not too far away. They found that of their 25 slides, 22 were located in a particular lithology, interbedded quartzites and phyllites. And phyllite is a very foliated rock, and its layering makes it less able to resist stress. It's much weaker, so in river cliffs, phyllites were the ones that were washed out. So 25, we had 22 in that situation. 2 were in ordinary shales. The big question is how much of the area were covered by these things. 2 were just loose debris in river terraces, presumably due to undercutting. But only 1 in hard, nice, hard granitic rocks. So geology is having an effect. You look at the structural things, 14 of these were due to the geological discontinuities, 9 they linked to faults, and 5 to adverse planes in the rocks. That's quite a useful graph. Graphic, I don't know who I pinched that from. That's a good. People worrying about earthquakes at the University of San Diego, I think. Shrink swell. If you get weathering, particularly, or if you've got natural clays, a lot of clay is a weathering product. Clay is a strange mineral structure, layers of aluminum silica that can pull water in and hold it, so it becomes part of the crystal. So when you wet them, they expand. If you let them dry out, eventually they contract again and dry out, and that's what causes these soil cracks. Now, this kind of cracking provides access to water and lines of weakness too. Another problem you get due to the mineral composition of the debris. This is another classic case study, again, a very big issue in places like Sweden and Norway, where they have glacial clays, very fine materials. And most clays are held together by electrical chemical bonds, but these are only bonded mechanically. Which means that when you subject them to an earthquake, or some other sort of disturbance of that sort, the mechanical bonds are all broken, and the stuff flows. They call it quick clay. And it's an engineering nightmare to deal with. In most clays, the bonding is electrical chemical, it's long range. That's why clays will stick together when they slide. Why you can mould the clay and it doesn't fall to pieces. And that mixed with water could behave like a sort of sticky plastic or sticky fluid. And it's due to the minerals, smectite, sillites, montmorillonites, famous one, clay minerals, tend to be implicated in this. Past landslides, yes, we've been through that again. The case study there, an old one, in the Pittsburgh district in Nagaland, where there was a big slide that killed people. But what they were was slides from the Quaternary, a landslide, great Quaternary landslide complex that had become reactivated. I don't know if it's true here, but it's a matter of observation. In Uttarakhand, most of terraced agricultural fields are actually built on landslide deposits in embayments, because there's soil, loose material work, and there's water. Both of those situations are, of course, hazardous. Tension cracks upslope. This is very common. I think Professor Rowett joined me at a place called Caerplan when he came to Wales. And you walked out of the front door of this and you could see one of these developing in the car park.
And the owners got very upset with me because I'd start my field trip in their car park, telling them how the whole building they were living in was on the freaking sliding down the hillside. In the event, they got so annoyed they put a big buttress wall and stopped the process, but at least we're on. But there you are, this is a bit of the road sliding away. So they didn't build the road down there for a friend who asked about that last time. It is going down on its own. And you can see the next line of slippage beginning to develop here in the cracks. Okay, so that's the head scarp and the tension crack as you see it in the road bed. What they're actually formed by, of course, are sort of pre-runners to landsliding. Like those first few rocks on the video that I showed you. So they're making the way. The smaller movements are gradually creating a slide plane underneath where the whole block will go. And the tension crack probably, if you're lucky, limits the upper limit of the forthcoming failure. So if it's big enough back scar, then things will fall into that as well. The role of water is critical when it involves seepage through these cracks. And in this method, it's the pressure of the water that matters much more than the quantity. Okay. Seepage through the slopes, classic examples here. There's water coming out through the Day-3, that's a big problem. Water is very rarely evenly distributed through slopes. If people map the groundwater table sometimes as a flat surface, but in detail, it's anything but. It says quoting to the wrong units there, but that's what it is too. But most rocks are full of spaces, voids. The porosity can easily be 30-40%, so the actual weight is about 1.9 to 1.6, unless you fill them with water. Water's density 1 gram per cubic centimetre, kg per metre squared. So if rock becomes saturated, well, it's easy maths to work out how much heavier it's going to become. The extra weight is gravitational stress on the slope, and that may be all you need. Deforestation. Something people don't realise, but tree roots actually have greater tensile strength than steel. You can test it in the lab to prove it if you don't believe me. They also have a very dense network which can cover many miles, and if you're lucky, they penetrate down into bedrock. Some trees have tap roots that will actually go into bedrock. That's not 100% positive, but they do it. I've seen landslides on rock falling on road cuts created by pines growing and prizing the rocks apart. But the trees do other things as well. There are barriers against rock falls and small debris flows. They're like putting obstacles in the way, and that helps. They reinforce the soil, particularly the fine roots of 1 to 20 millimetre diameter, form a net through the soil. They're interlinked. Many layers. And as you saw yesterday, they tend to move as a block together as a result of that. After forest harvesting, landslide risks increase, not immediately, usually, but within about 3 years when the roots begin to go away and it persists until the roots recover. It takes a few years for the big roots to rot. You may think you've got away with it, you're just getting surface erosion, but the landslide will follow when the roots begin to go. Interesting, a lot of the sediment is moved by landslides after deforestation, involves the removal of deep forest soils, because the trees are also building soil underneath it. In forests in Nagaland, you can sometimes find a metre of soil, whereas in grasslands you've got a few centimetres. And that's the difference. So your trees are also creating the material that's going to form these surface landslide slips. Once it's gone, and landslide rates decline. What was this slide for? Oh yeah, this is an estimation from that nice book by Seidel and China.
No, it's from the earlier book I cited. He reckoned that landslide deforestation can increase landslide activity about 3 to 24 times, based on studies in the American Sierra. Of course, deep landslides, as people tell you, are totally unaffected by this, because this is all happening at the soil survey zone area, dealing with the top 2-3 meters. Anything below that. So forests have an interesting relationship, the landslides. They're quite good in other ways. They dry the soils, and the dewatering increases slope stability. But they also increase the depth of the soil, and the loose soils store moisture. This is the colleagues in Nagaland who wanted to create stream sanctuaries on hill crests by preserving forests there. And the argument people again said, well, but they're pumping the water out through deforestation. And the response was, yeah, but they're creating deep soils that hold even more water. Well, from a landsliding point of view, these things are, if you want to worry about stream flow, that's quite nice. If you're worrying about landsliding, you prefer that one. Moreover, moist, deep forest soils, because they hold moisture, accelerate weathering, chemical and mechanical. So they can contribute to your landsliding in the long term that way too. And there are other negative effects of forests. There's root wedging, which I've mentioned, loading, forests, and there's associated waters add weight. If you get wind, trees trap wind and carry it down through their trunks into the soil, and that creates strength that can weaken rocks below. And wind throws scars of trees can become landslide source areas too, because they're exposed places water can accumulate. So most agree on balance. Pros and cons again. Forests are a good idea. So we're nearly at the end of this section. Is there much vibration due to traffic or the possibility of earth tremor? Vibrations literally shake a thing apart. I'm sure you've experienced this actually. You drive along the roads of Nagaland. Probably your bones don't fall apart like mine do, but your vehicle is probably much threatened. Well, just as the vibrations are being transmitted into your vehicle and your body, it's going into the ground as well on the hillside. It's worth thinking about. And it resembles a little earthquake. Let's have a quick look at a case study. This is one that some of us remember all too painfully. It's our little survey from Pandacola through the new Lower Mile Road to the leprosy hospital in Almora. And this was a test area. And we did one of these surveys that I'm setting you up for here. But this is a 7.3 kilometre road that we were looking at. And we surveyed it so far 1985, 1990. We did that together, Professor, did we?
Yes. 95
as well? I think you were still in Nagaland.
Yes.
Yeah, probably. 2000, no. And 2010, you were very lucky not to be there. It's a steep slope. It's undergoing suburban development. A lot of it was former agricultural territories, forested in the southern part down here. And interestingly, about 108 landslides on the roadbed. And the interesting thing about it is, in spite of what I've said, it was more or less the same number every survey that was done. The only difference was the size of the landslides was vastly different. Locations were similar, but the size was vastly different. These are some of the results we were pulling out of this to build our predictions. You know, here we have the mean hill slope angle above the road cut, 22 degrees, standard deviation. If you don't know what SD means, then you need to stay back for the statistics primer. Angle below the road cut was steeper, we were on the upper convexity. Road cut height, a horrible 5.7, which is bit big. Road cut angle, rather steep, 64. You look at it, you think it's a cliff, but you put a measure, an angle measurement on it, it's not. Road width, quite variable. Bigger, more or less, where there's less landsliding problems. Narrower, with a high road cut on spurs, which is why embayments and spurs tend to have different but serious problems. A lot of retaining wall built, some of it surviving. Sometimes on the upslope side, sometimes on the downslope side. We have our geological dip. We have, like we looked at there, there's a discontinuities per metre. Vertical discontinuities and horizontal we divided into because we decided both were important. Looking at the number of joints in the rock that were enlarged. In this case it was about 30%. I should use percent there, I converted that to something else, that would be metres per metre. Depth of loose material on top. Amount of road bed affected by undermining. Loose scree down of the road bed, we're looking at the broader environmental effects there. And we basically looked at two styles of failure, rockfall debris and slumping debris, and these are the amounts of the road per kilometre affected by, metres per kilometre affected by each. So there we have basic little study results. As I said, we did one survey to look at the general situation along the road, and one survey to compare the situation at each landslide. And it's tantalizing because the statistics don't always confirm this. You can see what's different. This is the landslide. And you can see this is the where it's on average. And they are different. On average, there's more tree cover upslope, better ground vegetation cover, perhaps because it's not shaded by trees, and landslide areas. That's upslope of the road cut. Hill slope angle, relatively steep, that's quite clear cut, isn't it? Height of the road cut, okay, it's bigger where there's a landslide. Angle of the road cut, again, it's bigger. So the usual suspects are there. As usual, there's a huge difficulty explaining, however, you could not join a dotted line down there and say that's the threshold for landsliding, because you find a big range of variation on either side of these things. I haven't included the standard deviations on that. But here you have them with the standard deviations. You can see there's quite a large range of difference. So one fits neatly into the other categories. Standard deviations describe within 60%, 66% of the mean, I think it is. Tree cover up, tree cover down, rock joint discontinuities. Strangely there you see that there's a huge overlap. The numbers are very similar and there's a big variation. The difference is not significant statistically, and if you don't know what statistical significance is, then you need to come to my remedial lecture in a little while. This is or the landslides, and I'll have to work that out. It's probably about the same for the non-landslides. They won't pair. Here we have 0.002, and that's probably close to a threshold of significance if you're going to run a lot of tests. So I usually accept one chance in 100 or one chance in 1,000 as being indicative that something is really important. Okay. This is a very poor diagram, but one that came to hand. So again, using statistical methods, in this case correlations. LQ is the volume of the landslide, and you'll see there's a huge correlation with apparent dip. 0.46, which would be highly significant. I haven't put the significance levels on there. correlation coefficients vary from 1 to 0. 1 is a perfect correlation, which means the variables are the same. 0 means there's no relationship between them at all. 0.46 means there's quite a strong relationship, a very strong relationship. Now what else can we look at? True bearing of the dip. Just annoyingly, there's also a strong correlation by chance with the amount of the landslide. I think this is the length of the landslide correlates with the volume. Many of the variables just correlate with other variables and don't do anything. There's our old friend slope. Correlates, of course, with the height of the road cap and also with the tree cover, but doesn't make a nice correlation with volume in this particular case study. I think it's from my early studies on the Surrey Road. But that's the kind of information you get by using the method of correlation, which again we've been talking about already. Okay, so this is a reminder of assignment 3, which I'd like you to. Sorry to miss your television programs and this evening, but at least you can talk to some of your friends. So alone, if you must, in the team of 3, I prefer. You can share the mark. It would be better probably because 3 brains are better than 1. Write out your research plan for a project to predict how much landslide debris you have to clear from a stretch of hill road. And think of that field trip yesterday to the stretch of hill road that you have in mind. Page 1, sketch out your multiple working hypotheses as we have done. Page 1 and 2, control variables that you will measure. How are you going to measure them? And why? And this also has bearing on that. In the last part of page 2, write how much data you're going to need, remembering that you need at least 30 samples of each category to avoid having to use statistics. And bearing in mind, the bigger your sample, the more likely it is you're going to get a statistically significant result. So how much data will you need to collect? Basically as much as you can stand. If you can't collect all the population, we did 108 on that stretch of road, but roads here could have many more. If you're going to pick the road from Deepapur to Kohima, you will have thousands, maybe tens of thousands. You can't measure all of them. How will you sample? And then finally, what statistical techniques will be used to analyse the results? Sometimes it's useful to collect your data. It's good to know what you're going to do with the data when you've got it. It's much easier that way than producing data and not knowing what you're going to do with it next. Yeah, that happens a lot as well. It's nearly as common, and it's more common probably than collecting variables that you don't need. Okay, well this is my end.
I have a request to all the participants. They can use the technology of mobile. You can take a photograph of this and follow and write.
We'll save us printing the sheet there.
Click on your mobile and click this photograph. This is the use of technology we have.
Yeah, they've been doing that.
They all have done.
First, before we go on holiday to Central America for a little while, we'll talk about Nagaland a lot, so let's look at someone else's problems. The more I travel here in Nagaland, the more I realise what a very beautiful and wonderful place it is. The natural beauty here is quite astounding. I also realise how delicate the environment is here and how sensitive you are going to have to be to apply development without destroying this place. So where is this leading? Well, okay, you're all educated people. You're all educated in the environmental sciences. So why is it on fieldwork I see 1 or 2 people throwing plastic bottles out into the environment? This is not really very respectful to the environment. But what is in their mind?
Do they think the plastic bottle will go to heaven? No. It makes just the world a little bit more like hell for the rest of us. So I have a special request. Please don't do it again, at least while I'm watching you on a field trip. Please don't do it again, ever. I don't often respect my Honourable Vice-Chancellor, but one I did respect, and for this one reason. I was walking into work late one evening, and I found him in the quadrangle picking up litter that some students had discarded. And I thought, well, this fellow is the real thing, he cares about this place. Alright, that's my little moral talk. Let's leave it at that. Oh, and if you see your friends doing this, do talk to them. The biggest problems in the world, it's why I've changed from doing much of this study to doing education. The biggest problem with this world is not the environment, it's not environmental change, it's the human mind. That's where it all is. Somehow we've got to change it, make it more sensitive to what it's doing. Each and every one of us. Off your soapbox, Martin. Let's go to Central America and a country that's very beautiful like this one, but has as many problems as well. Get this up. Here we are, Honduras. We've got Mexico up there, and America, and the United States, neighbours are El Salvador, Belize, Guatemala, and Nicaragua. And stuck in the middle, the poorest country of this group, Honduras. It's got flat coastal plains, but like here, it's mainly mountainous. Like here, it's got a subtropical climate. But unlike here, it has no cultural depth, no roots. It's an archetype we call the Banana Republic, because basically the economy is based on producing bananas. Became independent from Spain, and the big difference from here to there is lack of social cohesion and organisation. Population is 7.8 million. A huge percentage is very young. It's counted very poor for the Americas. I'm sure these figures cannot be correct. I read that off the internet. But you are not 10 times poorer than... In fact, people here are living in more comfort than people in Honduras are. So that figure must be wrong. Land is 10% arable, notionally, but a lot of it is farmed from shifting cultivation. And my point of contact with it was Hurricane Mitch, which destroyed some of my projects, as you will see, and killed a lot of people and caused a lot of damage. Okay, let's... Oh, what's happened? Help! Does the cable come out? So this is half an ideal. Maybe we're not going to Central America after all. The big problem in Central America is not one I think you've got here. Why there is shifting cultivation there now. Previously, the population was very low and people were farming the flatlands, growing maize and beans, basically, the staple crops. But then, let's say, globalization began to reach Honduras. A lot of people are very poor, grasp of the land, and big landowners laid claim to huge amounts of land and sold it to companies to do commercial cash cropping. And of course the government is very keen on that because the cash crops produce foreign exchange revenue, which they want very much. Unfortunately, if they pay anything to the people who are living as peasant farmers on the land, subsistence farmers, they pay very little. and that money soon disappeared. So they had to go somewhere. Good agricultural lands were all taken, so all was left were the hills and the forests. So you have people moving into hills and the forests who do not have thousands of years of tradition of jump, but who've just thought of the idea in the last few years. So of course they do it pretty badly. And the devastation is, in places, it's quite horrific. So this is the difference. In the meantime, more and more people are being pushed off the land. There are more and more young people who need land. The only way you can get land, you cannot get it legally if you're they call them campesinos, the subsistence farmers. You have to just get some land, clear it, and hope nobody throws you off. And what's been happening over the years, they started farming steep slopes, 20-30% slopes. And what's that in degrees? 15 to 20 maybe? And now gradually they've been pushed up to slopes which are more like cliffs, 65 to 70% in places. So they can only farm them by hanging onto ropes. Now of course, the soil erosion that's being produced by this, beyond all the other problems, is just gigantic. So the project I was involved with, which was funded by the UK government and was carried out by my trusty research student, he did all the hard work. I took all the credit. No, I didn't take all the credit. I hope I didn't take all the credit. But he did all the hard work. His name was John Helene. And he went to set up a project to look at how we could stop the soil being washed away from the hills. The classic soil and water conservation project. And his particular interests were live barriers. Cross-slope barriers. I noticed here you use trees cut from jump to make cross-slope barriers. His idea was that you could use vetiver grass and plant that in rows along the slope between your new crops, and this would hold the soil in check and gradually build up little terraces, which would be better for agriculture. So that's the story so far. We've got some land. He's a great negotiator, is John. I wish he were here to tell you the project by himself. I could take my name off it. But, where were we? I cannot even see my folder now. Maybe it isn't come up yet. Oh, it's close. So he approached the local forestry authority who had a research station that wasn't being much used because of financial cuts in the south of the country, and asked for some land to do his study, his PhD research on. The land was part of a hillside at the back of the site. The way he did the research was interesting. He asked local farmers if they would cultivate the land. He said, you can cultivate this land for free, no one is going to bother you. You can take all the crops. We will make scientific measurements while you do it. And that was the deal. It seems to have worked very well. Can you find my folder on there yet? I'll have to use the memory stick. It's a folder with GIAN 207. It's disappeared. There it is. Top one. Case study one. Oh, we'll be back in business. This is actually a photograph of the site that we were using, the test plots. And it was important because officially it shouldn't be farming on slopes above 20% in this part of the world. It's illegal. But in fact, most of the campesinos are forced to farm. No one had done any studies of how to protect the soil in those areas. This is familiar. Not done as neatly as here. Nobody's stacking wood. Nobody's putting logs across the slope. But they burn the forest anyway. There's a picture from the hills down at the bottom there. It's where there's actually a huge Israeli melon farm down the bottom. And these are the hills which the campesinos have retreated into. Today it's common to get farming on very steep slopes, and even steeper slopes are being forested and farmed. This is not unusual. You can see that's a live barrier going into place there. This is our test plots. These are the less steep ones at Santa Rosa, which is down in the south of the country near a place called Choluteca, at the end of the Choluteca River. And the way that soil is being collected, I was not terribly happy about, is by basically catch pits with occasional recorders on some of the sites, sort of recording runoff from little flumes. The standard test plots were 24 metres by 5 metres, two slopes we've studied, 35 to 45, 65 to 75, both of which were close together and on the side. There we are, that's the steeper slopes. These are the catch pits. There is a flume covered over to stop other water, and that feeds into a barrel with a measuring gauge on it, an automatic one, to find out what's going on. Each plot, 2 treatments, waived, cultivated with or without live barriers. This is a standard sort of PhD setup for this kind of business. If you're in agriculture, you'd recognise it. There's John Helene himself. This is a live barrier as you see it in the crops, between the rows of crops, and here's the corn coming up. Farmers are not necessarily keen on having too many of these because it takes up land that could otherwise be growing corn. So they have to be persuaded. That's the way you collect the sediment. It's being fed down into these boulders. There's John Helene working hard as usual. 3 years and 5 harvests between 1996 and 1998, and it was terminated by Hurricane Mitch. It's John Helene negotiating with one of the actual cultivators. There's the supervisor sitting around watching while the student does all the work. This will no doubt be a totally alien concept to you. And here are some results. Annual soil loss, 17. It's worth making a note of that. 17 tonnes a hectare per pre-Mitch. Results weren't what we expected. They're not what you'd get on less slower slopes. Different things are happening. So there was no significant difference in the amount of soil collected beneath either of the plots, or the treated versus the untreated plots. And technically, the textbooks tell you there should be significant differences in all those categories. But no one's looked at slopes as steep as this. And I think on steeper slopes, different things happen. Then the excitement. We had Hurricane Mitch hit us in October of 1998. Gosh, that's 20 years ago now, isn't it? 896 millimetres of rainfall. That's a heck of a lot. It's really extreme intensity. I don't know if you match anything like that here. I hope for your sake you don't. Maximum intensities are sort of off the scale, but we're in Britain. We've never seen anything like this, of course. Climate there is relatively gentle. That's actually Hurricane Mitch is the backdrop for this. There's some of the results. Floods everywhere. The Choluteca River's shifted its course by 1 kilometre at the lower end. That's incredible damage everywhere. Massive floods. These are the flood sediments that were put down during the thing. You can see where the floods had gone up on the sides here. There's a car there, of course. That's why that's done there. Landslides, and small and large, people being washed away. It was a real havoc for a few days. This is just outside Tegucigalpa, which is north of where we are, but it's the capital of Honduras. And they have a landslide block here that's come down and unfortunately taken out a part of the town. Huge 6 million cubic metre rotational slump. It's another case where there was a thing, the volcanoes, well, we saw the debris flow from there, didn't we? And this is a debris flow, of course. There's lots of loose stuff on top of a volcano from the ash that comes out. So they can mobilise, and here you have a huge mudslide coming down. Unfortunately, a town got in the way. Casitas volcano. You're blessed with no volcanoes in Nagaland, I hope. And landslides everywhere. Everywhere you looked. Landslides on all the hills. And unfortunately, landslides on our test plots. In fact, a huge proportion of the crops in Honduras were lost as a result of the hurricane. And in fact, we were the same. We lost most of our crop to landslides. But the interesting thing was that all the landslides started on the steeper slope. The gentler slopes were damaged, but the steeper slopes developed these things. Where we lost crops on the less steep slopes, it was because it was buried in the landslide debris. Look again at those landslides. We've been passing grass barriers, but there's John Helene again, standing in the middle of a landslide, and you can see that the depth of the shear plane is way over his head. There's no way little grass roots are going to stop something like that. Only trees might do it. Or in fact, all the landslides started from slopes which have been recently deforested. The casualty figures. After May, 5 to 20% of the local hills were all under landslides. On our trial plot, we lost 50% of our maize crop on the steep slopes due to burial. 3/4 of the maize on the steeper slopes. We had 5 landslides on our test plots. They had scars up to 2 metre deep and affected 70% of the test areas. No landslides originated on the 35 to 45 slopes. Damage was all due to the landslides from the steeper slopes, some of them above and outside our site. But they've all been cleared of forest and planted to maize in 1997, just before this had happened. So it's a classic case study. If you have a heavy rain after in this sort of season, it can have the same effects here probably. This was the interesting result though. This was the annual soil loss by surface erosion, things Soil and Water Conservation Departments worry about. This is the soil loss from the landslides. So the annual landslide sediment yield was 600 times greater than the average annual soil loss. The recurrence interval for Hurricane Mitch is suggested to be about 300 years. So doing this was giving us false protection. The real source of erosion was actually landslides. Maybe twice as much, it just didn't happen so often. So our conclusion, which nobody in the Soil Conservation Department liked very much, was on the steepest slopes in the longer term, it should be defending against landslides and worry less about everyday soil loss to water erosion. So we're into an issue which affects us in landsliding too. This is the magnitude versus frequency conundrum. is the problem of our having a short time duration. We think 600 years is forever, but in landscape terms, of course, it isn't. 300 years rather. The event we can deal with as a society tend to be the ones that happen regularly. And much of our environmental protection is ordered to 1 in 50 or 1 in 100 year events. Our big questions to ask, though, are when does protection against the short-term damage actually create a bigger problem when it's overwhelmed by a larger, less frequent event? How often do the weaknesses in which we base our data calculations, because our records don't go back 100 years, probably they certainly don't do here, they don't barely do it in the UK. I'll show you what this means, not by looking at the landslides, because I haven't got the data, but the USGS has been working on the floods at Choluteca, where there is a gauge. Okay, the peaks discharged during Hurricane Mitch, people estimate was this, 15 cumex, 15,500 cubic meters per second. Yeah, that's the number. The highest flood previously recorded, in 50 years of record, was just 2,000 cumex. 50-year flood discharge estimated by projection of the data from the river gauge was 12,500. That predicted by local historical data, 56 years, was only 5,000. But the USGS in their wisdom took 4,600. That's what? A bit more than a quarter of the actual Hurricane Mitch discharge to define their 50-year flood hazard maps. Okay, well that's great. But now you go to Choluteca and people say, okay, I'm not going to build my house on the 50-year floodplain because it can be destroyed. But if I go just above it, I'll be fine. And development is trusted on maps. So a 51-year flood, recurrence interval flood, is going to hit a lot of them. They think they're safe. People don't, but in fact, their safety is an illusion. It's interesting, isn't it? It's one of the dangers of hazard mapping again. I wanted to bring this in earlier. And these things are still happening. This is Hurricane Ida, which is next door in San Salvador. Same problems, loads of landslides, loads of problems, same sort of response. Okay, so I haven't run too much over time, despite the excitement. I should say, those of you who don't want statistics, this is optional. Some of you said that you did, so I'm going to do a little statistics workshop on basic statistical methods. If you want to go out and take the fresh air or something because you know all this stuff, I don't mean to trouble anyone who's only sit here if you are not happy with statistics. Even basic statistics. I'm not going into high-level statistics, okay? This is, let's get out of this. And we'll move through it very quickly. It will be, come on, we are slow today. Okay, optional basic statistical methods is what we're doing. Those of you who are students here, of course, there's a colleague who's a statistical geographer who will know much. Probably he should leave and close his ears, actually, because this is muddy boots statistics we're going to do. Oh, that's the wrong one.
go back into familiar territory. Our beloved Himalaya. That's not what we're here about. Basic statistical methods. We went through this in the main series. It's about numerical characterization and prediction of the behavior of populations of landslides is what we're about. And its statistical method is used because it's objective, removes bias. Statistical methods are simply tools. Some people are terrified, but they are just tools. If you go to a mathematical department's statistics course, they will show you how to design all of these and what the mathematical construction is. Here we're just using them. We don't want to build the hammer or the mobile phone ourselves, we just want to use it, okay? And we're going to use it for several things: to simplify and describe data, to find associations between the variables that we measure, to prove that those links are meaningful and not due to chance alone, and to show trends over space and time. Golden rule in statistics, and if you go to the research journals, you'll find people using really fancy methods. Well, you don't use really fancy methods when a simple one will do it for you. So what that means is they've got trouble in their data, okay? Or they're showing off. So, best rule for statistics is keep it simple. 6 simple things that everyone can do. You can describe data. And one of the key ways of describing it is using the standard deviation, which we'll talk about. You can look for trends in the data. And the key word there is regression. You can look for similarities between variables. And the key word there is correlation. You can look for differences between 2 sets of data. And usually we use things like t-tests for that. Or you can look for differences between the frequencies of categories, where you're not using data at all, just how often something occurs. And finally, you can say if the relationship you look is significant. And that little expression there means that the probability is smaller than 0.05, less than 1 in 20. And that's the gold standard for a single test. If you've got P equals 0.051, that's not a significant relationship, so you might want to massage that if that's all you had. Descriptive statistics, well, everyone knows what an average is. It's also called the mean, the arithmetic mean. You can also talk about, if people don't, the mean deviation, which is the average of the distance everything, other results are about that mean. The median is just the middle number in a series. So if you've collected 100 measurements and put them in rank order, which is a good thing to do anyway, then number 50 is your median. The mode is the most common record in a series. So if you're measuring little landslides, it's probably, lots of little landslides, it's probably going to be a relatively low number. There won't be many huge ones in your data set. So in that data series, the mode is 3. In this data series, the mode is 17, just because it's in the middle of the series. Many types of measurements, unfortunately not all by any means, including a lot that we deal with in landslides research, have a similar type of frequency distribution. If you're throwing darts at a dartboard, you're going to hit target quite a lot. Very rarely you'll be way out and miss the dartboard altogether. And mostly you'll miss in the sort of, be close to your target. So all that does is express that. That's the normal probability. So you can consider the results of a load of researchers measuring slope angle using the same clinometer. They'll all get slightly different results. If you average it out, you'll get one number, but the individual results will be scattered all around it.
The point about the normal curve is that errors are symmetrically distributed about the mean. And the majority are small, few are very large. The distribution is called normal, and it's the foundation of a lot of stats. It's quite useful because it tells you 68.26% is within one of the data, and normally distributed sample is within one standard deviation of the mean. And it's used for statistical calculations because very small percentages are more than 2 standard deviations from the mean, and certainly very small from 3. Okay, the standard deviation you attach to your average normally to describe the variability about the dispersion of the data set about the average measure. That's the way it's used most. Okay? People also use the standard error of the mean, which looks at the variability between sample means you get from taking many samples from one population. So a larger standard deviation will often have a standard error. Standard error is quoted much less. You can note that it's there, but don't worry about it for the moment. Standard deviation is what you want to put in all of your papers. Put an average and a standard deviation. Unfortunately, not everything is normal. One version I had for my students said not everyone is normal, but never mind. There are many common types of data distribution. We've looked at the normal, but it can also be log normal. And so if you take the logarithms of the number, you end up with a normal distribution. There are some other classic distribution types, Poisson and binomial and many more. That's the log normal distribution, and you can see that it's skewed to the left. And it's very common. A lot of variables, including slope angle and wind speed, tend to have this kind of distribution. That isn't normal in itself, but if you use the logarithm, just change the metric, then you can normalize the data set. I've had scientists who ran screaming from the room about when you do that as well, but in fact that's a standard process. You can do anything to your data set as long as you do it to all to normalize it, and if you can use a wider range of statistics on it. You can take the square root, square it, divide it by n, do whatever you like. And this process is called data transformation. And you use it because many of the strongest statistical tests only work on normal data. And sometimes data is only not normal because of the way you've measured it. Some scales that you use to measure, like slope angle in degrees, are inherently not exponential factor built into them. So do a lot of ordinal variables, like the earthquake scale, wind scale, and the rest of it. If all else fails, if you put your data in classes, you can sometimes normalize it that way as well. In which case you don't use the individual data, you translate it all into different classes of data. But the message is that you can transform data to normalize it. This is the Poisson distribution. It's getting close to what you get with landslides in volumes and things. Debris flows, earthquakes, most of them are close to this scheme as anything else. But you have to use statistical methods when you're dealing with them that don't require normal data. Okay? So that's an inhibiting factor. Okay, we've talked about description and the types of data distribution. Let's talk quickly about inferential statistics. And you're doing this is the real business end of it. Because it's about testing hypotheses. It's about the comparison of data sets. And really, it's only about 4 questions you can deal with. Which interests you most depends on your research hypotheses. You might want to know, do the data variables correlate? Do they do the same thing? Or negatively correlate, do the opposite thing to each other. One goes up, one goes down, that's a negative correlation. Can you draw a straight line, or if you have to, a curved line between them? Is there a trend in the data? Often you're looking through time, or you're looking through a sequence along a road, you want to find a trend along it. Could the two samples have come from a single population? So you've collected landslide data and non-landslide data, could they all be the same thing? Whereas actual landsliding made a difference. That's the sort of test you need to know. And are the differences between two sets of data significant? In fact, use similar tests for these two. As with our research, when we started off the research exercise, most statistical tests are looking to reject the null hypothesis. And the null hypothesis is that the differences between your two sets of data, or your two variables, could be down to chance alone. And you want to prove that it isn't. Well, you have to do that by proving that it's infinitely improbable that it's due to chance alone. And that's an example of the alone. Testing the null hypothesis. So you're testing that the real difference between the means is 0. That's essentially what it comes out of. If there is an observed difference, how often would it happen? By chance. If it's less than 1 in 20 or more times, that's probability equals 0.05. Then you've got a good argument that you can reject the null hypothesis, and only on that time, only, did I say only? Probably I meant only. Can you use the word significant? You may run into a tutor who will throw out anything you call significant you can't prove as being statistically significant, particularly if you're playing with numbers. That's highly likely. You don't have to look just for 0.5%. The smaller that number is, the stronger your argument. So you'd like that 0.00005, that's much better. That means you've got 1 in 10,000 or 5 in 10,000 chances that it's due to chance alone only. So that's your actual, you can't really get below, larger than that and really make a sensible statement, but you can get that number lower, you're in really good shape. Okay, 14 techniques you need to know. Regression is about detecting trends. Correlation is about detecting similarities, positive or negative. Chi-square, these days you can use the Fisher exact test, which is much better, and you can get off the internet and you have a calculator. It's very difficult to calculate by hand. For comparing frequencies, the usual comparison is observed versus expected. So if you expect, you can make a hypothesis, on average there should be 1 landslide per kilometre according to government figures, and you find there are 1.6 on average. Is that reasonable, are those frequencies what you'd expect? In these tests you always use frequencies, never actual numbers. How many times, not how much. How many times, not how much. Novices go out and they misuse this all the time. And finally there's the t-test. Okay, some people prefer logistic regression, but the t-test is the old gold standard for looking at differences in data tests. And these two are especially nice because neither of them require normal data. There are two types of statistical tests. A lot of the big fancy ones are parametric tests based on actual data values, but they use a distribution which is not significantly different from the normal curve. Most computers will give you a routine to check whether a data set is normal or not. Non-parametric tests, the statisticians turn their nose up at because they consider them baby tests, but they don't require data to be normal. and use a parameter which exists for any distribution. So basically, the problem is most multivariate tests tend to be parametric. So if you're comparing 2 or 3 variables at once, you tend to be trapped there. But if you're only comparing one or two together, one with a standard distribution or 2 together, non-parametrics, probably the way to go. There we are. Parametric tests need data that fit the normal curve. And the base standard of parametric correlation is the Pearson correlation, which is parametric. Let's talk about that. If things increase together, you can say they're positively correlated. If one increases, the other decreases, they're negatively correlated. Correlation coefficient ranges from 1. That means you've got the same variable, basically, if you get something as high as that. They're the same. If it's 0, they're completely unrelated. Most of the time you're working around somewhere between, and you need to have your significance value to know whether it's important or not. This is the Pearson problem moment correlation, and it's always signified by the letter R. Sometimes you see R squared used, but R. This measures the linear relationship between 2 normally distributed variables. It is the benchmark correlation coefficient. If you can use it, use it. Most common. In fact, most people call it the correlation coefficient. And it is the basis of most multivariate statistics. The non-parametric correlation coefficient, one I use a lot in my work, is Spearman's rho. That's rank correlation coefficient. This relationship again between 2 variables. You can use it with ordinal data, which is very rarely normal, with interval ratio data that's not normally distributed. In fact, it takes happily wants any sort of data. It doesn't deal with categorical data. You've got to have at least an ordinal scale to play with it. Normally, Pearson's rho will be a little larger than Pearson's R, except in an exact linear relationship, and in that case both are equal, or when R outliers exist, hence to exaggerate R. But functionally it's pretty much the same. Good reasons to use non-parametric methods. They're much less restrictive. You don't have to prove normality. They're less fussy about the data you put in. Some even use nominal scale data, chi-square is an example, because you're dealing with frequencies. Easier to compute, you can do most of them by hand, and the sums are very simple to do and understand. It's a good idea to work it out by hand before you use a computer. Power tends to be a little bit lower when data is normally distributed, but the rest of the time it's much better. So they're good things. This is what landslide data looks like. And one of the things you want to say, well, is there a trend line I can put through this so as place becomes ungrassed? That's not where that word ungrassed came from. I think I made that up. Can I say there's a trend there? The answer is maybe. The trend to use regression, this is a simple straight line regression. Y equals x, A plus bx. It's a technique that models the relationship between 2 or more data sets. It's a simple graph. A simple regression links 2 variables. Multiple regression deals with several. It's additive. If you wanted to multiply the relationships, you have to take logarithms of everything, and then it treats it like multiplication, because if you add logarithms together, you're multiplying. Linear regression deals with straight lines. Curvilinear regression uses curved lines. But if you've got a curve, you really need to know why it's curved. And if you don't know why, then stick with linear regression. Sometimes these lines can be linearized in curvilinear cases. as by a logarithmic transformation. That's the commonest transformation you will use in this area. So here's an example of the statistical approach again, the one we looked at earlier. That's telling you the strength, that's the R squared, telling you the strength of the correlation. It doesn't tell you how significant it is, which it should do and could do. So I'd have sent it back to the office if I were reviewing it to do that. That's the actual equation for the line. And this is an application of it. The way the regression techniques work is they minimize the square of the differences between data points and line. And they tend to put a best fit line in. Sometimes you'll see people quoting about the goodness of fit of the line, and that's what they're talking about. That's the difference between a linear regression and the log linear version. It's y equals ax to the b. And those little simple power functions are everywhere in your data set. They're everywhere in the natural environment. You could almost do a whole course on fluvial geomorphology, river geomorphology, just using that equation in various agents. Chi-squared, goodness of fit or association, comparing frequencies. The traditional version compares what you expect, which would be your control, versus what you've got. You can also use it to compare two samples. You can also use it to compare a control with a test area, and I am running out of time. How often, never how much, that's it. That's the most common mistake made with chi-squared. Goodness of fit. T-test. This is the final big one that you need to know. You've got two samples to compare. You can use a t-test and it gives you a very easy and reliable statement of results difference. Technically it's a parametric test, but if your sample is greater, that's the wrong way around. Greater than 30, the data must be normal. Another reason for testing a big sample. One-tailed test you can apply, which is gives you a better result, but only if you know which way the difference is going to go. Otherwise you use the two tests. The F-test is something that you can use to determine if they have the same variance. It does need interval or ratio data there. There are alternatives. You can use a test called Whitney or Wilcoxon if you're dealing primarily with ordinal data. And they're non-parametric, very simple non-parametric tests. So t-test is the bog standard for establishing differences. What you need to do is select the test that answers the right question for you. Correlation if you're looking at associations. Chi-square if you're looking at frequencies. T-test if you're comparing means of numbers. And trend if you're looking at something varying in time or space. You set the hypotheses. When you set the hypothesis, as I've asked you in the exercise, you set the test that's appropriate to it. And you collect data for that test. If you've got t-tests, you know what that means in terms of sample size. There are other useful tests. Wilcoxon signed ranks is the easiest. Mann-Whitney. Kolmogorov-Spirnov is especially used for tests of normality. And there's a nice technique called partial correlation. Partial correlation you only need a computer to do for you. But what it does is hold one variable constant and looks at the variable of variation of two others, the correlation between two others, if you take that out of the problem. And there are so many variables that are closely linked on landslide studies that sometimes it's a handy thing to know. Probability, we've talked about that already a little bit. P equals 0.05 means a 1 in 20 chance. 0.1 is 1 in 100 chance. I like to use that as a threshold because I intend to run a lot of tests. That's really good. How do we explain it? It's easily worked out. This was done by a colleague of mine here. It's not like I pinched it, but it's called a parachute contest. Look over here. You've got a parachutist jumping out of a plane. He doesn't control his direction of fall. Beneath him, the land use is 85% agricultural land, 10% manure piles, compost, and 5% is a rose garden. What is the probability of him landing in compost or coming up smelling of roses? Okay. Well, 1%, 0.1, that's a tenth is manure, and 0.05 is roses. So in landing in both, the probability is 0.15. That's the basis of which all these probability things are worked out on. Because there's a 0.85 chance that he will land in agricultural land. When you start comparing, adding probabilities together, things get more interesting. So you've got two parachutists jumping out of a plane. You want the probability of one landing in the, we'll call it compost, and one landing in the bed of roses. So at the same distance, it's 0.1, a tenth of the land is manure piles, and 20th is rose gardens. So you've got two parachutes. So in order to find out what the joint probability is, you have to multiply. So you multiply 0.1 by 0.05, you end up 0.005, which means it's almost impossible. That's 5 chances in 1,000. You could do it for landing in agricultural land too. So one's in the roses and one's in the agricultural land. Again, that probability is quite small. It's getting close to being reasonable, 0.0425. The important thing is to remember that in two cases like this, you multiply the probability. Non-Ferroni correction. Most science and most statistics books only look at one test at a time. But we're dealing with multiple working hypotheses in the social sciences and environmental sciences. And of course, if you run multiple tests, you increase the probability that one of your results will be due for chance alone. If you run 20 tests, yes, there's a 1 in 20, it's almost certainty that one of them will have a wrong result because there's a 1 in 20 chance that they will do, just due to chance alone. Bonferroni divides the level of probability by the number of tests. So technically, if you're running 20 tests, you multiply 0.5 by 5 and end up with 0.001. The problem is, this can eliminate a lot of data that you consider individually significant. Have you happened? I've had those situations where you've only got one test result that you have considered significant, and it's above that. So you have to, there's all sorts of literature on this, but the idea is that you take your threshold for recognizing significant as low as you can do it without it being too painful. And I hope all the mathematicians and statisticians are outside the room at this point. But that's what happens in practice, right? I'm not here to talk about theory. Bonferroni correction. There's also a Bonferroni practice. There we are, that's the practical advice. A way around this, because if you'd only taken the one test and another test, you probably accepted 0.05 as probability. So a way of getting around that is by calling it possibly significant. Okay? That's distinct from significant. I think I've finished. I hope I've finished. I can't remember what else this goes on. No, that's it. I hope that was helpful. It was rushed through rather more than I would do. Normally I'd have you plodding around doing little studies with it, but it was a remedial thing. Does anyone have any immediate questions? Have you even time for immediate questions? No.
Any question, query? Time is here for 2 minutes. Please.
I think the basic rules are that about 4 questions you should ask. You know those 4 questions. When you record an average, try and record a distribution around it, a standard deviation. Makes you look more professional, and it helps people understand how strong your average or mean is. If you're using multiple tests, think about Bonferroni and try and take a lower level of significance. And plan ahead so that for whatever test you're going to use, you have the right sort of data for it. Fitting the data to the test is better done in advance than